I am going to discuss how Master's theorem can be applied on a decreasing function in this video. We can also use the Master's theorem formula directly when the recurrence relation between the subproblems is a decreasing function. Here is the sample recurrence relation is given here for the decreasing function. T of n equals to a is going to be the coefficient T of n minus b plus f of n, where f of n must be n par something. Theta of n par k, like the functions done, the number of operations performed outside the recursive call, the cost of work done performed outside the recursive call is what this f of n is. So k is the power of n is going to act as a k here. The condition is a must be greater than 0, b also must be greater than 0, and k must be greater than or equals to 0. When it comes to decreasing function, there are only 3 cases are there, only 3 formulas are there. If you have to compare only with, you have to check only the a value. If a value is lesser than 1, this is the formula, and a is equals to 1, this is going to be the formula T of n equals to theta of n par k plus 1, and if a is greater than 1, then the formula is T of n equals to theta of n par n by b into f of n. So only these 3 formulas we are supposed to remember. Let's discuss few examples under this. First example, T of n equals to T of n minus 2 plus 1. Let's write the value a value. A value here is the coefficient, which is 1. B value is the decreasing value, this is the b value. B value is 2, it must be greater than 0, yes it is greater than 0. And k value is n par something should be the k value, there is no n here, no power here, so k value here is 0. Now based on the a value only we should decide which formula we are going to apply out of these 3 formulas. Here a value is 1, which means case 2 is applicable here, case 2 is applied. The formula is T of n equals to theta of n par k plus 1. So theta of the complexity is going to be n par, k value 0, 0 plus 1 is 1, which means the complexity is theta of n. Let's discuss another formula. T of n equals to T of n minus 1 plus n. Fetch the values. A value is 1, b value is 2, and k value is here n power 1 is there, so k value is 1. Check a value is 1 only, which means case 2 formula is applied. So case 2 formula is again theta of n par k plus 1. So the formula is n par k plus 1, k value is 1, n par 1 plus 1 is 2, so n square is the complexity. Let's discuss one more example. T of n equals to T of n minus 1 plus n square. Now let's write these values. A equals to 1, b equals to again 1, sorry here b value is 1 because n minus 1 only here, and for a change, sorry, the question is T of n equals to T of n minus 4 plus n square is the question. Let's imagine a value is 1, b value is 4, and k value is 2. Now check which formula is appropriate here to apply. Check a value is equals to 1, which means again case 2 is applicable here. So case 2 formula is T of n equals to theta of n par k plus 1. Theta of n par k value is 2, 2 plus 1 is 3, which means the complexity is theta of n cube. So if you observe these 3 examples which I have given, the similarities are there is no coefficient here. So when there is no coefficient, it is going to, which means the coefficient is only 1. If the coefficient is 1, blindly we can go with the second formula, right? A equals to 1. If coefficient is 1, simply if you observe here, if you take the first formula, first example, coefficient is 1 only, the complexity is n. If you check your f of n, it is 1, and let me change the color. If you check f of n value, it is 1, and if you check the final complexity, it is n. Check second example, again the coefficient is 1, check f of n, it is n, and the answer is, the final complexity is n square. In the third example, f of n value is n square and the final complexity is n cube. If you check all these three questions, the a value is 1 only, which means the coefficient is only 1. Here what we can observe is, when the coefficient is 1, blindly we can multiply n along with this f of n value, and that is going to be the final complexity for the decreasing function. Here f of n is 1, 1 into n is going to be the final complexity. Here again coefficient is 1, check f of n, it is n into n is going to be the final complexity. Again check f of n is n square, so f of n into n is going to be n cube is the final complexity. When the coefficient is 1, irrespective of this b value can be anything. This decreasing function can be anything, 1 or 50 or 100, it can be anything. When the coefficient is 1, you can simply multiply n with f of n value, and that is going to be the final complexity. Right? Let us discuss few more example also. Okay. Example number 4. Already we discussed the 3 examples. Example number 4 is t of n equals to 2t, there is a coefficient now, 2t n minus 2 plus 1. Fetch all the values. A value is the coefficient which is 2, b value is the decreasing value which is again 2, greater than 0 only, it is satisfying the condition, and check k value. K value is n power something, there is no n here, so there is no k value here is 0, and f of n value here it is given as 1. Okay, check which formula is applicable. A is equals to 2, which is greater than 1, apply third formula. Case 3, formula is t of n equals to theta of n power n by b star f of n. This is the formula. Substitute the formula. Theta of n power n, b value is 2, so n power n by 2 star f of n value is 1, which means the final complexity is theta of n power n by 2 is the final complexity. Let us discuss one more example. Fifth one, t of n equals to of 1 by 7 star 1 by 5 t of n minus 1 plus n. This is the recurrence relation. Fetch all the values. A equals to 1 by 5, b equals to 1, k equals to n power, there is 1, okay, 1. F of n values n. Check which formula is applicable. Check a value is 1 by 5, which is lesser than 1, right? So case 1 is applicable. Case 1 formula is t of n equals to theta of n power k. So theta of n, k value is 1, which means n only. So the final complexity is theta of n. This is how the Master's theorem can be applied on the recurrence relation, which follows the decreasing function as well. So this Master's theorem is the very easiest way and quick way to derive the time complexity from the recurrence relation. And few limitations are also there in Master's theorem. So we have already seen various examples of analyzing the time complexity using the Master's theorem. But do you think that we can use it for any function in the given form? Actually, the actual answer is no. So like, what are all the drawbacks then? What are all the limitations you are facing on Master's theorem? Number 1 is, already we would have discussed in the previous video, while solving the dividing function using Master's theorem. So, we faced one example where the a was not constant. So, when it comes to the Master's theorem limitation, there are, as far as I know, there are two limitations. One is if a is not a constant, it cannot be applied. If a is not a constant, Master's theorem cannot be applied. Time complexity cannot be analyzed using the Master's theorem. And the second limitation is if f of n is not a polynomial, again we cannot use Master's theorem here. For example, t of n equals to 2t n by 2 plus 4n. Here f of n is exponent, so Master's theorem cannot be applied. For this example is already we discussed, it is 4 power n t n by 2 plus n log n. If you check here, a of n is not a constant, so here the Master's theorem cannot be applied. So, these are the Master's theorem's limitations. Thank you.